And then, like I said, the Grignard reagent will react with all sorts of things. And one of the things that it will do is it can react with parts of your molecule you don't want it to react with. And so this is the first time that we're really talking about this, but we can actually protect parts of our molecule if we don't want them to react. And it's a little bit uh, there's a lot of different ways we can do it. And actually, there's lots of publications, and there is actually a big, huge book called The Greens Protection. I don't remember if that's exactly the name, but it's a big, thick book, and you can look through and find, all right, does this look kind of like my reaction, my molecule? Can I use these kinds of things to protect my molecule? So here's an example. Let's say I wanted to do a Grignard where I wanted to use this Grignard to react with this ketone. But the, the problem is that Grignard I want to use has an alcohol in it, so it would actually react with itself. So let's talk about the Pinnacle reaction. And it's the Pinnacle reaction or Pinnacle rearrangement is actually nothing that you haven't seen before. You just haven't seen it kind of through this lens. So I can take virtually any compound that is a vicinal di, like a tertiary vicinal diol, and in the presence of an acid, I can get a rearrangement. So on your mechanism sheet, you can draw this mechanism down, but essentially, it isn't anything new to us. We're just putting some information that we learned in Organic 1 kind of together. And so these groups can be any carbon groups, really. So I'm just using phenols here, but it could be methyls or propyls or anything like that. And this reaction happens in the presence of a catalytic acid. So this is actually important that because this is going to come back up, the fact that it's a catalyst that will kind of help us figure out what's going on. So this is a catalytic reaction, and we can protonate our alcohol. And again, remember, this doesn't have to be phenols, it can be other things. Please take a note of that on your mechanism sheet. I just used R groups. Now I have made that OH group a better leaving group. And I want to point out that very few times do I focus too much on whether, too many reactions are equilibrium processes, only because everything's in equilibrium, but this is specifically important to note that this is an equilibrium reaction because what I'm going to do right now isn't necessarily extremely favorable, neither is it not, right? So my leaving group can leave, but it isn't more or less stable than it's staying on there and just going back to what it was originally. What's going to drive this mechanism that we'll see later is our product. So a question that you should ask yourself is when we get down to my next couple of steps is why does this even happen? So on my compound, I do have the ability to undergo a rearrangement. And so the question we should ask ourselves is why does this even undergo a rearrangement? Because I'm going from tertiary to tertiary. And that's a very good question. In Organic 1, especially if you had me, I stress that going from tertiary to tertiary isn't really helpful. However, it's not that it doesn't happen or can't happen. And I'm going to draw this a little bit differently. If we draw the resonance structure, it is the resonance structure of this intermediate that actually helps to drive us to why this happens. So if I look at this resonance structure, I have a plus charge on the carbon, a plus charge on this oxygen right here. So I have resonance structures. And so yes, this can go back, but what drives this reaction is this last step to stabilize this reaction. And this reaction actually won't go backwards at that point. And because of this, right? And remember I said it's catalytic, so how do we get acid back? That's where my water comes back in and deprotonates. And so I've done this exact reaction before, and it actually works extremely well. It's you have to heat it up a little bit, but it works fairly well, right? So it's an acid-base protonation of an alcohol. Um, Now the hydronium leaves, we get a rearrangement. And so the question should always be, why am I going from tertiary to tertiary? However, it's the product. It's the product that drives the equilibrium. It's pretty stable, and it's not really going to go back the other way fairly easily. Now, it's not that it can't. It does a little bit, but it can't. It's fairly stable, and it's usually going to be a solid in the reaction conditions that we do. All right, so now we're in our next chapter, and let's talk about some things related to ethers and thiols and things like that. A lot of what I'm going to talk about are kind of actually just related to each other, so I may actually just skip over certain comparisons. So, for instance, comparing um, the SH2, it would have very similar, not exactly, but similar bond angles as water, etc. So a lot of same things apply. Now, thiols can't undergo hydrogen bonding, but they do undergo very strong dipole-dipole attractions. And so our water can undergo strong dipole-dipole attractions. And we also know that OH groups, they're not very acidic. They have pKa's probably close to about 15. So one question I want you to think about, thiols have a higher pKa, thinking about Ario. What factor drives why thiols, SH groups, are more acidic than alcohols? In class, we talked about the Williamson ether synthesis, and I want to revisit that a little bit. And so we can deprotonate a alcohol to form an alkoxide, and then we can react it with a primary, secondary, tertiary. Not really, won't work. Benzylic or allylic will probably work because they work for everything. You can use that. The secondary is very, very slow. So my question is, I can do this reaction and I can get this compound, but if I, and a lot of times we can interchange what the alcohol is and what the alkyl halide is. And so here is an example where I did that, but this reaction doesn't work. So a hint is why, thinking about this is an SN2 reaction, why doesn't it work when I use that tert-butyl iodide? Now, I also just want to kind of say this way. So let's say I have this molecule. There are two ways that I could make this molecule. I can have my alcohol as ethanol plus my alkyl group. So I can have ethanol and I can have propyl with some leaving group on there. And I can do that because the nucleophile can attack once I make the nucleophile, and I can get this product. Or I can start with propanol as my starting material with an ethyl group as my electrophile. And I can actually come up with different scenarios. So when we go back to that previous question, remember this is tertiary and this is SN2. So the question was really asking you, why can't you do this? And it has a lot to do with tertiary, right? Another thing to kind of consider is that when we talked about protecting groups, ethers can actually be protecting groups. They don't really break down too much in the presence of a base, but they can be broken down quite easily in the presence of an acid. So if I were to give you, well, not terribly easy, you still have to heat them up, but if I were to give you dialpha ether, in the presence of an acid, I can protonate that alcohol, the oxygen, sorry. And by doing that, I can make this thing leave fairly easily from the other side. Now this actually breaks apart even more if the groups that you are using are secondary. By being primary, this is going to be very slow and you need heat. But you can break this apart because now this is going to be easy to break off from one side. So that's why they're reversible. All right, let's move on to another reaction that you've already learned in Organic 1, which is oxymercuration, demercuration. And at least if you had me, I talked about that was just a generic reaction that we focused on. We can actually use different nucleophiles. And so instead of an OH for oxymercuration, I can use an alcohol, and all it does is put the OR in that position. I could also have put a nitrogen, and the nitrogen would go in the more substituted position. As long as there's a hydrogen on whatever the nucleophile is, I can do that. I can put sulfurs there. And so if my nucleophile was, let's say, ammonia, my product would be an amine. If I had used, let's say, this thing, I could get a product like this. So pretty much whatever we use for an alcohol in this and this Markovnikov, whatever we use to make the alcohol like water, we can replace it with any nucleophile as long as it has a hydrogen to do the same thing. All right, a couple more notes before we move on a little bit. That we're not going to spend a ton of time talking about ethers. Why? Because there isn't a lot of things that they do. We can use them, we often use them for solvents. We can use them to chelate things if you have a special kind called a crown ether. But other than very acidic conditions, they don't really do much. That's why they're good for protecting groups, they're good for solvents. One exception to that are epoxides. So you learned about epoxides in Organic 1. Epoxides make good leaving groups. Epoxides can open up because of ring strain. So the bond angles are actually very strained. And so it's easy to open and break apart. And so we treat this oxygen like it's a leaving group. It leaves from one of the two carbons. So it can leave from carbon 1 or carbon 2. And so it makes it easy and favorable to be attacked by some sort of nucleophile. So when you were in Organic 1, you learned that you can open these up under acidic conditions to get a diol. And so that's what we're going to talk about. This is kind of probably the most important reaction for epoxides. Looking at this mechanism, we have a nucleophile and it attacks one of the carbons. And so here we're saying that this isn't symmetrical, so it doesn't matter which side. And the good thing is that you can actually open your molecule up and add any sort of nucleophile. It can be a Grignard, and if you add a Grignard, you're just going to make a longer carbon chain. So Grignards are going to form carbon-carbon bonds. If you added a reducing agent like LAH, you're going to essentially make an alcohol because you're adding a hydrogen here. You can add an OH, an NH. You can add all sorts of things. So we can actually add multiple things. But the key here is whatever you're targeting is in a vicinal position to whatever that nucleophile is. So we can have all sorts of things on this molecule, but that's the kind of thing that you're locked into. So that nucleophile can open up the oxygen, then we can protonate it, and then once you protonate it, you get that alcohol. So that's what we had here. So it's essentially an SN2 reaction. So here's an example where we take methoxide, it opens the ring up, and then you can get your OH group and the alcohol, methoxide and the alcohol on opposite sides because it's an anti. That's why you can get an anti-diol because an OH can attack on opposite sides. Sulfur can attack, OH can attack, anything, any nucleophile can attack. All right, so there's two more aspects to the opening, the ring opening. If you use a strong nucleophile like what we saw before, strong nucleophiles are going to react fast And because they're going to react fast, they have a tendency to go to the less hindered part of the epoxide. So if we look at this right here, when we use a strong nucleophile like a methoxide or your thiolate, or you have OH groups or anything like that, even though they all still add anti, they're going to add to the less sterically hindered side. So here we have a tendency to add on this side. Now, if you have a tertiary group, so here it's between a primary and a secondary. If you have a tertiary versus a primary, something interesting happens. And when your nucleophile attacks in the presence of a acid in this case, the first step is the acid protonates this, so this becomes a good leaving group. So then it's not as much of a issue of whether or not you have less sterically hindered or not when it comes to protonation. So every time we have a strong nucleophile, as long as it's not like crazy, like sterically hindered on one side and then a weird, sort of semi-sterically hindered on the other side, as long as it's like very obvious, like primary versus secondary, primary versus tertiary, a strong nucleophile will always have a preference for the less hindered side. But when you protonate first, the oxygen not being a good leaving group now becomes a good leaving group. And so then we actually change some dynamics. And this is where thinking about your transition state of this mechanism starts making sense with what's happening. And so when we're in the, so if we have this nucleophile, if it's a weaker nucleophile, and we have protonated our epoxide, it's easier for the nucleophile wanting to go on the tertiary position because it's more stable. And so if I go back here and think about something that I learned in Organic 1, when something reacts fast, this is a kinetic process. But once I did that protonation, I've lowered the energy it takes for this ring to open. So my activation energy actually has dropped. This is more of a thermodynamic process. And in terms of where the nucleophile will attack, it will attack giving us the most stable transition state. And it's going to be on the tertiary side. Now, I'm only saying this because we're comparing primary and secondary. Secondary and tertiary are a little bit complicated because you might get mixtures of products. So our last thing is that we see, last couple things, we see epoxides in a variety of different places. Like for instance, one place that we see it is actually in the synthesis of bronchodilators. And here we have a nucleophile that can attack an epoxide, open that ring up, and then we can eventually protonate that oxygen and we get this new carbon-carbon bond. And with a few more steps, notice that in this drug, this is the molecule that you have here. You have this oxygen next to that nitrogen. This is actually very common in things, in some of these drugs. This actually, epoxide ring opening is actually very common in drugs in general. We also see this in something called a prodrug. So sometimes when you take a drug, the drug is only active once it changes its form in your stomach. And it does this as a protective way of protecting the drug. So you put the drug in a way that it kind of has like a protecting group on there, and under acidic conditions will open up like a ring or change it. And so epoxides are actually used in some of that. The last thing I'll talk about really, really quickly is that ethers can be made into these ring kind of structures, and depending on the size of the structure, we can have something called molecular recognition, where the size can recognize different kinds of ions. So for instance, this is used for chelation to trap certain ions, and we can trap a variety of different other molecules in there, and depending on the size, it can recognize when something is present. So that is one example of where we see ethers. We also see ethers in a lot of reactions because they're inert in the reaction. They don't do anything in the reaction, but sometimes help to stabilize the reactants. And so we oftentimes see them for that